Hello everyone, welcome to the second part of Hamiltonian Formalism. In this video, I'm going to uncover some of the hidden mathematical structure behind Hamiltonian Formalism. I'm going to show you guys why Hamiltonian Formalism is very elegant in terms of mechanics, and also I'm going to show you some of its advantages over the Lagrangian formalism. This video is going to be very mathematical because it's actually a mathematical physics topic and also involves a lot of concepts in differential geometry. But I really recommend you guys to learn this part because I think it's really good. It's really helps you like prepare for the learning of quantum mechanics, because some of the operations you do in here are analogous to those in quantum mechanics, and I'll explore that in the later part of the video. Okay, so in my previous video, we talked about the basic logic of Hamiltonian formalism. What is Hamiltonian formalism? It's just a change of function from Lagrangian function to Hamiltonian function, and what comes along with it is the change of the equations from the Lagrangian equations to Hamiltonian equations. So the core change is the change of the independent variables. We change from the generalized coordinates q and generalized velocity q dot to qp, which are respectively the coordinates and the momentum. At the same time, the function changed from the Lagrangian function to Hamiltonian function, and the Hamiltonian function takes the form of this. If you look closely enough, you'll notice that first of all, the value for the Lagrangian function is of course a real number because the action is defined as the integral of L over time. So of course, since it's integrating over time, we have to make sure that the value for L should be a real number. And also, I think I talked about it in the last video. The value for Hamiltonian is actually equivalent to energy. So the value for Hamiltonian function of the system is actually representing the total energy of the system. So of course, energy itself is it's a real number. Yeah. So okay, so let's see what these two terms will bring us. So first of all, Q is generalized coordinates, and Q is lives on the configuration space. So Q is the configuration space, and Q belongs there. And of course, Q dot will belong to the tangent space at point Q, and we denote it as TQQ. Okay, so since Lagrangian functions independent variables are q and q prime here, and q belongs to the configuration space and q prime belongs to the tangent space of configuration space. So actually Lagrangian function works in the tangent bundle, which is denoted as TQ, which stands for all q in the configuration space, and TQQ. And this is called tangent bundle of the configuration space. So that's where L works in. Okay, so after changing the coordinates, we notice that the new variables become Q and P. We already knew that Q lives still in the configuration space, doubtlessly, but we don't know where P is. So we are looking back to this equation, and we have, as I already said, that both of the values for Hamiltonian function and Lagrangian are both real values. So that must so with that being said, PQ prime must be a real value thing as well. Here we can actually view P as a function of Q prime, since it's always like eat out something that belongs to the tangent space of Q and space out something in the real space out real number. So actually what we call the space that P is in, we call that home TQQ R. So this notation represents that the all linear maps that projects something on TQQ to R, and that's essentially what this means. And this space is also called the dual space of TQQ, and we denote it by adding a star on top of it. It's called dual space. And since Hamiltonian function deals with all such Q's and P's, so it's actually essentially working on the space. It's actually essentially working on the tangent bundle of Q, TQ star, and that's expansion of this. There's one thing to note about all these spaces. So we just mentioned that TQ star is the dual space of TQ. So the vectors living in these two different spaces are actually related. So for the vectors living in TQ, we call those vectors contravariant vectors. Like those living as a generalized velocity q dot. So they are contravariant vectors. Here's how it's defined. So let's consider like there's a configuration space, and in the configuration space we have two different sets of coordinates. One is small q, and the other one is big Q. So obviously the two coordinates could be transformed to each other through some sort of transformation, and we want to analyze how the two sets of different coordinates are correlated. So we consider a geometric object called x in configuration space, and we can represent x in either small q or big Q, like this. And okay, so now we want to see how these two are related, how these small q and big Q are related, and so we can take the derivative of x over time, and either in small q or big Q. Here we can use the chain rule to expand this term. And now we would discover that this term and this term are the same. So we would yield small qi dot is equal to partial qi over big qi times big qi. And that is equivalent to this. Qi dot. All right. So we call the variables that transforms under the form like this, we call that contravariant. So the opposite of contravariant is called covariant, and the covariant vectors lives in the dual space of the space we just talked about. So that's actually like in this example we use the example of generalized velocity, which lives in TQ. So the dual space of TQ is TQ star, which we just mentioned, and that's where momentum lives in. So momentums are the covariant vectors, and we call that covectors for short. So, and you guys can derive by yourselves, but if we like apply the same set of changes from the coordinate changes from the small q to big Q, momentum transforms in a different way, or opposite way, like coordinates. So you guys can derive yourself. So when small q transforms to big Q coordinates, and the momentum, let's say it's p transformed to p prime. So the p prime would take the form like this. And you could see that. Oh, sorry, we missed the indexes. So yeah, you guys can discover that this coefficient and this transforming coefficient are like the reverse of each other. So that's how contravariant vectors and covariant vectors are like opposite. The reason why I talk about contravariant vectors and covariant vectors is kind of like giving you guys a hint, because notice here that in the Hamiltonian we have p times q dot. So we just showed that the transformation of generalized velocity and momentums are like the reverse of each other. So if we times them together, the two coefficients will cancel each other out. So what this implies is that the value p times q prime is actually independent on the coordinates. So no matter what coordinates we choose or what kind of transformations we apply, we will always get the same value, because the two transformation coefficients will cancel each other out all the time. Okay, without further ado, I would like to move on to the main stage of today's video, the phase space. I would like my video to be logically natural, so I don't want to talk about symplectic structure now, since it's a requirement for a 2 form. I would like to talk first about the 1 form on the phase space. And the 1 form is actually kind of special because it's called tautological one form. So the feature of this 1 form is that its definition is independent on coordinates chosen. Actually, it's hidden in the word tautological because in English it actually kind of means like intrinsic. So like this is natural, and it's independent on coordinates. So first, let me show you the definition of this 1 form. And here's the definition. So the 1 form is denoted as theta, and the definition may seem quite abstract, but I'm gonna explain it in detail. So first of all, since it's a 1 form, the 1 form acts on the tangent vectors of that space and spits out a real number. So first of all, we must define a tangent vector. So we first pick a point at the phase space, and which we call that space Z. Z, and it lives on a phase space, and it has a value Q and P. So I want to note here that this ordered pair it represents a point, and it's not coordinates, it's a point. So because I just mentioned that the tautological 1 form does not depend on coordinates, so yeah, so this is a point, not a coordinate kind of thing. So first the point Z is a point in the phase space, and then we pick the tangent vector at that point. We call that V, and it lives in a tangent space at point Z of the phase space. Yes, it's called T, and it has TZ and cotangent cotangent bundle. Okay, so far we already know what's the thing that the 1 form takes in, and then we now move on to the right side of the definition. So the first thing we used is something called pi. So pi is called a projection operator, and it's also naturally existing on the phase space because what it does is simply selects the q value of the point. So let's say like let's operate pi on Z. And since Z is the 2 values for Z is Q and P, it simply spits out the Q value. So it selects the Q value. It's kind of like if we have a vector on the XY plane, and this is a vector on the XY plane, and the operator simply spits out the projection of the vector on the x-axis, for example. So like this thing, the length of this. So that's like a very natural projection definition on the phase space. But now here we take the differential of this operator. We turn it into pi star. The reason why we do that is that because we want to act it on V, and V is a tangent vector on the phase space. Yeah, so we take its differential. I'm not sure like what exactly it's called, but in some texts we call that take differential. In some texts we call it something else. But anyway, I think you guys get the idea. Anyway, so after taking the differential, we takes the tangent space of both sides. So we take something on the tangent space at point Z of the phase space, and we project it onto, since the pi thing selects the Q value, so we will project it onto the tangent space at point Q. At point Q. Yeah, and this is how the differential of pi will do. So yeah, after we have already done the pi, we have to put V into the differential of pi. We'll get something on the tangent space at point Q. But eventually, what a 1 form does is that it takes something it takes the tangent vector of phase space to a real number. So in the end, we have to find something that projects from TQQ to the set of real numbers. And what's that operator? So as I just mentioned at the start of the video, that's essentially what P does, right? It was essentially what P does. So yeah, so the last thing we use is P. Okay, so let's review quickly what this definition essentially means. So first of all, we find a tangent vector V, and then through the natural projection operations differential pi star, we first V is something on a tangent space. It belongs to TZ, T star q, and then we after we do the operation pi star to it, we get something that belongs to the tqq, and eventually through the p, through the operation of the momentum, we'll get something on the that belongs to the set of real numbers. Yep, and that's it. That's how tautological one form is defined. So the reason why I said it doesn't, the definition of it is independent of coordinates, is that the pi star, both of the pi star, p, everything that is encompassed in this definition exists naturally on the phase space. Yeah, so it does not require the existence of coordinates. Okay, now that we already shown that the tautological one form theta is a universal geometric object that naturally exists in a phase space without requiring the existence of coordinates. Let's now expand it under a set of coordinates to see what the expression actually look like. So we pick the normal coordinates that people will normally choose. We expand under the set of just under generalized coordinates and the momentum coordinates from q1 to qn and p1 to pn. And since v is in a tangent space, so v could be expanded as this. Here's the basis. The basis vectors are tangent vectors as well. And we now put v into the differential of pi first here. So that would, since pi, the differential of pi would only select the q counterpart. So after we put this into pi star, we will yield this counterpart. Yeah, we have to pay a little bit attention to the expansion of p here, because the p we use is actually something that projects something in TQQ to R. So we must ask ourselves, what is, since p belongs to the since belongs here, we must ask ourselves, what is the basis of this space, the dual space of TQQ? So since the basis for TQQ basis is obviously this, the dual space, as I just mentioned, the dual space must projects the basis to a real number as well. So the TQQ star basis would be the direct differential of q. The reason for that is that this when this basis when the basis of the dual space acts on the original space, it will result in a real number, which is Kronecker delta kj. So yeah, this is a real number, and that satisfies the requirement. So the basis for the dual space of TQQ is this set of bases. Okay, and then we sub this back in, and so p will be expanded as another index k, pk dqk. Okay, and we sub this all back into the definition here, this definition equation, and we will try to derive the expression for theta. So theta zv is gonna be equal to first p, then pi star. The result here we have and we could simplify that, because as we just said, this when this is operates on this one, it will result in a Kronecker delta, and which could be simplified and to cancel out the either k or I. So here I cancel out the k. So yeah, and we keep this, because if k is not equal to in the cases where k is not equal to I, this thing will result in 0. So yeah, we can keep just one index. Okay, and now we try to guess what is the expression for for theta. In my opinion, I think the expression for theta is kind of easy to guess, because all we have to do is only simply throw out the coefficient of b here. So that is equivalent to saying that the expression for theta must contain something with dq. Yeah, because we want to cancel out because q is independent with p, so dq and p would result in a 0, and but in the same time we are keeping the q here. So here we have a Kronecker delta, and so yeah, the answer is quite easy to guess. The answer is sigma I pi dqi. Yeah, that's the answer. And you guys can try to sub this back in and or operate it on v. The answer is same as what we get here, piai. Yep, and yeah, here's the expression for the tautological one form that expanded under the standard coordinates. Okay, now that we have already established a one form, the tautological one form, we can now move on to a two form by taking its exterior derivative, and we call this two form omega. And that's where the symplectic structure is gonna start to appear, and we obtain omega by taking the derivative of the one form d theta, and operation d follows the Leibniz rule, so like this. So df wedge g plus f wedge dg. It also satisfies that if you apply the exterior derivative for to a thing two consecutive times, d squared, you are resulting in a 0. Okay, so yeah, let's apply it to the expression of theta. And obviously for the dqi counterpart, you will obtain something like a d squared qi, and that term is 0 obviously. So the only term left is sigma I dpi wedge dqi, and that's the expression for the two form omega. The omega has satisfies the requirement of the symplectic structure. The first requirement is closed. For something to be closed, it must satisfy that its exterior derivative is equal to 0. So obviously in this case, d omega is equal to d squared theta, and yeah, as I just mentioned, there's a rule that if you apply 2 times, you're gonna result in a 0. So that's 0, and it satisfies the closed condition. And the second condition is called non-degenerate. So this requirement essentially is saying that the kernel of omega must be 0. So before we verify it, for those who don't know what kernel is, so the kernel of definition is this: omega is equal to the set of all u belongs to space V, and uv is 0 for any v belongs in big V. So for the kernel, if we're asking the kernel of omega to be 0, so for when omega is applying to any of the uv in the space, for applying to any v in the space, if the expression result evaluates to 0, the only solution to that is that u is 0. And that's a little bit like hard to verify, but we can establish a series of equivalences. So first of all, since the two form is both bilinear and anti-symmetric, we can transform it into the multiplication of matrices. So omega uv is equal to negative omega vu, since it's anti-symmetrical, we can transform it into the multiplication of matrices. You can say negative U transpose omega V transpose. Negative V transpose, and omega is gonna be the the matrix that is obtained by obtained through by applying the basis of U and V in that space to omega, like EV EU, and you are obtain kind of a matrix, and we call the matrix omega, and negative V transpose omega U, and that's gonna be 0 for any V in that space. So now we're asking the kernel of omega to be 0, and that is equivalent to saying, since this holds true for any V belongs to the space, so the only solution to the equation omega U equal to 0 should be U is equal to 0. Okay, so now we have successfully transformed this requirement to a classic linear algebra problem, and this condition is equivalent to saying that omega is invertible, which is equivalent to saying that the determinant of the operator should be non-zero. For those who find it hard to understand, you guys can view the matrix omega as a transformation that applies in the space, so like a rotation or a compression or stretching. So for example, let's say we have a cuboid in a space. If let's say if for all U that lies in this plane, they are all solution to the equation omega U is gonna equal to 0, we're gonna have a problem. Why is that? Because if all the points that are on this plane, they all satisfy this equation, you're destroying this cuboid to a rectangle, and that means you're turning a 3D thing to a 2D thing, and that is not compression, stretching, or rotating. You're like kind of like destroying the geometric object. So this is not invertible. So that does not like meet the requirement. And for the final equivalence, that its determinant is non-zero. A determinant is kind of like a factor for stretching or compression. Like if the determinant is equal to 2, like you're actually what the operator does is like stretching the vector by a factor of 2, things like that. So if the operator is invertible, that means that it belongs to like compression and stretching. So this thing should not be non-zero. Okay, so yeah, that's okay. Now, so this is our final simplified condition, and we can verify that more easier than the kernel thing, and we'll do the calculation in the next page. Okay, now what we now need to do is just simply building up the matrix omega. So to do that, we have to find a basis to operate in. So let's put the 2 form in under the basis of V. So as previously mentioned, V belongs to the tangent space of M over here. So let's choose the basis of that. The basis is set of tangent vectors Q1 to Qn, P1 to Pn. And the matrix formed by 2 form should be 2 by 2 matrix. Yeah, if we're like dealing with I've already dealt with the indices. So 2 by 2 matrix omega. So this should be QP and QP on the 2 sides. So the first block, let's first look at this block, which is QQ block, and let's put the 2 basis vectors in, which is the partial of Q, let's say I, and the other one is J. Let's see how it goes by directly putting the values in. And here's the P, another index K, wedge DQK, and QI, QJ. So the calculation of two form is actually a determinant, since both the two form determinant are skew symmetrical. So yeah, k d p k q I j term and the qk dqi dqk dqj and determinant. This is kind of simple, since p and k are independent variables, so the above two terms should be 0, and the below two terms is gonna be Kronecker deltas ki and kj. And okay, now we can throw the k thing. That's gonna be determinant of. Actually, yeah, that's not necessary. Actually, this thing is gonna be 0, evaluated to a 0, because the determinant simply is like cross multiplication, and 0 minus 0 is gonna be always 0. Yeah, no matter what the values are. So yeah, so the first block, this one should be 0, and using the same set of method, we can obtain the other three elements, which are respectively the identity matrix, negative identity matrix, and identity matrix, and 0, and the determinant of omega will finally be 1. 0 minus negative 1, it's going to be 1, and it is non-zero as expected. So the second requirement, non-degenerate, is also satisfied. Now we have already successfully shown that the two form we gained from the tautological one form, omega, is a thing that satisfies the requirements of symplectic structure, since it satisfies the two requirements, closed and non-degenerate. Now you guys may be wondering why the two requirements are essential, and why it would be helpful to the Hamiltonian formalism, so why it would be useful. So now I'm going to explain it. So first, I'm going to explain the use of non-degenerate. So first, let me remind you of our ultimate goal. The ultimate goal is kind of like we want to find a vector field, a kind of vector field, because a vector field can essentially describe the evolutions of all the points in a space, because they are all tangent vectors, and tangent vectors could help us predict what can make our the motion predictable. So a vector, if we could use a vector field from the two form, it would be very, very helpful. And what is even more helpful is that the vector field obtained is unique, meaning that if we already have the omega, we can determine the only vector field that's gonna describe the system. So that's our ultimate goal, and let's see how the omega could help us. Let's see what we already have here. Omega is a two form. Okay, omega is a two form in the phase space. M is the phase space, by the way. We use this notation, and the big omega squared is the notation for a two form, and we also have Hamiltonian. Hamiltonian is a function that operates on Q and P, which is from the phase space to a set of real numbers. And vector field is a set of tangent vectors. A set of tangent vectors. So that's kind of tricky here, because we would like to obtain a vector field, but that's probably all we have. However, from H, we can notice that H is a projection from M to R. So what would DH make us if we take its differential? The DH would be from the tangent space T, let's say a random point P, TPM to R. And TPM would be exactly a tangent vector in the phase space. So DH would be essentially a one form on that. Okay, now here's the core part. So the core thing we want is a vector field and XH. So let's call it XH. So XH, the vector field is essentially the encompasses all tangent vectors. So it could be one of the parameters of omega. So and now we use an operation called interior product, or some people call it contraction, to make the two form into a one form. Yep. So this is what the contraction or interior product does. So let's fix one of the since two form the omega 2 form requires two parameters, and if we fix one of them as xh, and xh are, like I just mentioned, xh are all tangent vectors, so it could be one of the parameters, and we fix it, leaving the other parameter free. So this is essentially a one form because we only have that only requires one extra parameter, and we can equate it with the other one form dh. And here we got an equation of two one forms, and we can use this to solve the equation for xh. And for the convenience of notations, we define something as omega flat. And omega flat is essentially essentially one form, but just for the convenience of notation, it goes from TPM to its dual space. And its dual space is essentially from the set of all linear, as I just mentioned at the start of the video, a set of all linear projections from TPM to R, and that is exactly the one form. So we denotate this as the newly transformed one form. So omega flat xh is going to be equal to dh, and now we can obtain the expression for xh. Xh would be omega flat reverse dh. Okay, and as I just mentioned, our goal is to obtain a unique vector field, and let's see whether it's unique or not. So the we haven't used the property non-degeneracy. So we just show that omega is non-degenerate. So if we could show that the definition of non-degenerate is actually the same thing as injective, we can obtain an equivalence injective. And so since the dimension of TPM and its dual space is equal, both are 2n if the dimension of m is the dimension of m is n, the dimension of the two spaces would be both 2n. So with these two things, we can obtain an isomorphism. Since the omega flat is an isomorphism, we can determine that it's a bijective as well. So if we use its inverse and the corresponding value is dh, the corresponding vector field we eventually obtain would be unique, because the isomorphism would imply that the projection is one to one. Yeah. And now I believe you guys see why the non-degenerate thing is quite essential to Hamiltonian formalism, because that would help us obtain a unique vector field that could help us predict the motion of the system. Okay, let's now move on to the second requirement, closed, and see how it is useful. Before we talk about that, I'd like to first introduce a very important concept in differential geometry, which is called Lie derivative. Lie derivative is defined as follows. L is the notation for that, and x is a vector field. Oh, it could actually, in this kind of abstract definition, x will be indicated direction, to be more like specific, and t would be a geometric object and defined as this. The star means pullback, and phi t would be the flow generated by the vector field. So if you guys don't know what flow is, so if I have this equation, and it is determined by since vector field is vector field kind of like this describe the evolution of the thing. So, and instead of like tangent vectors, and if we're given that when gamma is when t is 0, gamma 0 will be p. So the phi t p would be defined as gamma pt. So yeah, this flow will take the point p to the time in this trajectory with that when time is t. So that's what flow essentially means. And so what this Lie derivative essentially does is that it compares whether it determines whether the geometric object t changes when the flow x generated by the vector field x x on it. Yet so we must compare at the same point. So we need the pullback operation here, and yep, that's essentially what the Lie derivative does. It just checks whether if the Lie derivative of something is 0, it means that this thing does not change or to be more specific, the intrinsic properties does not change if it's affected by the flow generated by the x vector field. So let's see whether the our generated Hamiltonian vector field xh and whether the flow generated by it will change the symplectic form, the two form. So let's calculate the value for this. The definition equation above given above is kind of like abstract, so we could not really use that equation to calculate it. But luckily, we have a formula called Cartan's formula that could help us calculating the value, the Lie derivative of omega. This derivation is kind of complex, so I'm gonna skip that for now. But the expansion of after we use this formula, the expression will become this. So the thing that looked like kind of like iota, it is actually the denotation for interior product. So it's essentially what we just talked about regarding the new thing, omega flat. So with this notation, it essentially means that if you're applying the interior product between xh and omega, we're simply fixing the first parameter of omega to be xh. So we can essentially like rewrite this equation without needing to define a new thing called omega flat. Instead, we can rewrite this as xh omega is equal to dh. Yep. All right. So okay, let's like expand it and see what we'll get. So the first term will becomes d squared h, and as I just mentioned, if you apply exterior derivative for 2 consecutive times, you're automatically resulting in 0. And for the second term, as I just mentioned, we just checked that the d omega thing is 0 because the two form is closed. So so here the second term is 0 as well. So the Lie derivative of omega in the direction of the Hamiltonian vector field is 0 overall. This property is of significant importance because first of all, it means that at the flow of time, as long as the system is Hamiltonian, the geometric structures brought by the symplectic form will be effective overall throughout, and yeah, such as the Poisson brackets brackets that we're gonna talk about later, and also other structures as well. Also, this property directly leads to the Liouville theorem, which we will not be covering in this video, but it's very important as well. And because since the two form, the geometric meaning of a two form would be an oriented area. So what the Liouville theorem essentially saying that the bounded area in the phase space is preserved by the flow of time. Yeah, and this is a very important conclusion as well. So yeah, so the requirement that a symplectic form must be closed came quite useful when we are like trying to calculate its Lie derivative, and it will result in a 0. So saying that the two form will remain unchanged at the flow of time. The next thing I want to talk about is the Poisson brackets, and this geometric structure is naturally brought by the symplectic form omega. So let's first consider a Hamiltonian system, and let's consider a variable f, which does not explicitly depend on time. So first, let's calculate the total derivative of f over time, and you will get an expression like this. Since it does not explicitly depend on time, it will depend on the generalized coordinates and the momentum. And with the Hamiltonian equations, we can rewrite the two derivative of Q and P. Minus Pi. Okay, and this is actually the form of Poisson brackets. We write this as a curly bracket f and h. And if you guys fully understand the definition of Lie derivative, since f is a function, is a variable in the Hamiltonian system, so its evolution over time would be exactly the Lie derivative of the function f at the direction of the Hamiltonian vector field, like that. So we want to connect the Poisson bracket with the symplectic structure, since actually the geometric structure came out of it. So how do we connect that? And since the since the Lie derivative means that the function f, the function f's directional derivative at the direction of xh, we can write this as df bracket xh. And with the same set of logic, we want to bring this back into a two form. So since we already have one parameter fixed, with this df, we can use the same type of logic over here, and we can plug this into the two form. And yeah, this time we can going backwards. We can generate a vector field based on the function f, xf, and we can plug this in the first as the first parameter. So what we get is omega xf and xh. There, we have successfully established a relationship between this two form and the Poisson brackets. So since these two concepts are connected, the Poisson brackets naturally inherited the properties of the two forms, such as anti-symmetric and bilinearity. Yeah, and also the Poisson brackets is very useful because as you're transforming from classical mechanics to quantum mechanics, this Poisson brackets is actually turning to another type of square brackets that is one very important step of quantization. So it is very useful. Next, I would like to talk about another geometric structure that is brought by the symplectic form, which is canonical transformation. And this concept is of significant importance in both classical mechanics and quantum mechanics as well, because it really helps simplify solving the pattern of specific dynamic problems, which we will see in later examples. So before we talk about canonical transformation, I would like to first talk about the concepts pushforward and pullback in detail. Actually, we already used the pullback operation when introducing the definition of Lie derivative. But here I'm gonna explain in more details. So first, let's consider a general example, a general case. So let's consider a mapping called f from manifold M to manifold N, and we can naturally find its differential because you're just taking the tangent space of both sides. So we can let's say P, the differential of f at point P, and P is a point on the manifold M manifold. So basically what the differential does is it projects a tangent vector of the M manifold called at point P, and you project it to the corresponding tangent vector at point Fp on the manifold N. So is pretty straightforward. And let's consider v as the tangent vector at point P on the manifold M, and it's pushed forward that x on the tangent vector is just the differential of f. So as you see over here, the definition is like that. So here's an example. A typical example of tangent vector would be the velocity vector. So first, let's consider gamma. Gamma t would be a curve or a trajectory in the phase space. It lives on the phase space, and so v would be v would be like a tangent vector at the manifold, and let's define v as gamma's derivative at when t is equal to 0. So this 0 means t is equal to 0. So this is like a specific point, and then on the M manifold, and you can define its push forward. So according to the definition we just introduced, so you first push it, use the mapping f to push it to the N manifold, and then you take its derivative to turn it into a tangent vector. So that's the push forward of a tangent vector. You could also use the push forward operation on the vector field. So let's say a vector field called x, and it operates on the M manifold, meaning that let's say we have a point P. Still, we have a point P on the manifold M, and the vector field x will push the P to the tangent vector at that point, which is x bracket P, and it belongs to TPM. So what if you want to use this vector field on the corresponding point of M on the manifold N? So there you will require the operation push forward, and yeah, the push forward operation will help you do that by defining the following operation. So first, you act the vector space. You use the vector field on the point P, like you're using the original. You acting on an original point. You take that tangent vector, and you use the differential of f to push that tangent vector xp to the objective space N, and that's how you define the push forward of a vector field. And yeah, so this equation is equivalent to the following one, because if you're just using another notation y, if you use the character y to as f of p, then you would define a differential at the reverse of f on y. So yeah, this is an exchange of notation. So that's the pretty much definition of push forward. It basically just helps you map a tangent vector, either a tangent vector or a vector field at point M, and help you help you move it to the objective space N. So okay, so another operation that's kind of like the reverse of push forward is called pullback. So remember I just talked about that push forward helps you get either a tangent vector or vector field from M to N. So pullback is often operated on K forms. So however, the pullback operation is getting a K form that operates on the N manifold back to M. So that's why we call it pullback. Okay, now let's consider a K form. It's called alpha, and it's on manifold N, meaning that it originally operates on the K tangent vectors on manifold N. So what if you want to you want to use this K form on the manifold N using the operating on the corresponding tangent vectors? So here you would need the operation called pullback, and you pull back. So the tangent vectors v1 to vk will be the tangent vectors at manifold N, because you want to operate on that. So you first will need to push the k tangent vector to the manifold N so that alpha could act on it. And so the corresponding point will be P, and here will be FP because f of P, because alpha is defined on the manifold N. So here's like the reverse of push forward. Instead of like you're pushing a tangent vector or a vector field on M to push forward to the manifold N, you're pulling K form on manifold N back to M, where it could be successfully used. So yeah, these two concepts will help us help us more like actually define what is canonical transformation. So here, canonical transformation. Canonical transformation is a type of passive transformation. It means that the system is the same set of system, but you're just describing it in a different set of coordinates, which could brought some to some degree of convenience. So the mapping involved will be, let's call it phi, and you will be from M to still M, because you're just describing the same system by using a different set of coordinates. And the requirement for canonical transformation is that the pushback of the mapping when it acts on the 2 form would be the same. So what the canonical transformation essentially does is that it preserves the 2 form, so as well as all the dynamic equations involved. So let's see why. Okay, so let's say the previous set of coordinates we use is small q and small p, and we transform it into big Q and big P. And let's sub this back in. So the new omega will be d big Q. Wait, d big P, wedge big Qi, and that will be equal to the O2 form dpi wedge dqi. The operation pullback obviously preserves the wedge product, because you want to act pullback on the K forms, so you must preserve the wedge product, since the wedge product means like oriented area or volume, so you gotta preserve the geometric invariance. So it would yield this. And also, the pushback thing is interchangeable with the exterior derivative, since you guys could verify it by pulling out the Stokes theorem in the in differential form, so you guys would understand why. And oh yeah, we used the Einstein convention here, but I just didn't write the summation sign, so we could further. Let's interchange the variables. And the pullback of dp and dpi, simply writing pi and qi in terms of q and p, because you're writing the new thing in terms of the order coordinates. That's essentially the definition of pullback. So that would be saying, oh wait, I should not write these over here. So that would be dpi qp wedge dqi qp, and this is equal to the old d small pi wedge dqi. Yep, so we have already confirmed that if this equation is satisfied, this equation would essentially means that the 2 form omega is preserved. So let's now verify that if the 2 form omega is preserved, the Hamiltonian vector field will be preserved as well, meaning that the form or structure of all those dynamic equations would stay the same. Okay, so the essential point is that we're saying that if the phi operates on omega, so we must confirm whether the Hamiltonian let's just derive how the Hamiltonian vector field will change. Okay, so the essential core equation we need to use here is simply the derivation of the Hamiltonian vector field. This you first you calculate the interior product between the Hamiltonian vector field and omega, and you equate it with dh. And after you apply the transformation on it, the dh is a one form. It will change after performing phi. You will get on the right hand side it's gonna be equal to d phi pullback dh, and since this is interchangeable with the exterior derivative, and let's denotate this new new Hamiltonian as h tilde. Okay, and let's look at the left hand side. Here we have to use a property of between pullback and push forward. So this is the equation we need to use, and it is it's general. It does not only apply to the Hamiltonian vector field, and its derivation goes as follows. You simply just, like, if you want to prove it, just expand the left hand side and right hand side, and discover eventually for the right hand side you discover that the reverse you will discover that the reverse of the differential of f on the point P will cancel this one out. You will get like simply you'll get simply an identity function, identity projection, and and you just cancel each other out, and you will you could successfully prove that the equation holds true. And if you apply this equation on the on here, you could rewrite it as this: push forward xh. Okay, and then we use the property of canonical transformation, and we sub this here. We will yield and so then you could see that if the right hand side, so you equate the left hand side with the right hand side, you will yield this equation. So you could see that the new Hamiltonian vector field, like, let's write it as x h tilde, would be since the form of the equation is preserved, it's still the same form as this original equation. So the new Hamiltonian field will look like this. And from this you could see that it simply is the push forward of the reverse of phi, and so everything in the Hamiltonian field, the average structure of the Hamiltonian vector field will be preserved. So yeah, that's what canonical transformation does. So the advantage of the canonical transformation is simply that you could, for example, let's use an analogy here. So let's say you have the xy plane and you have like two vectors, but if you rotate the axes, the y-axis and x-axis, you rotate it counterclockwise 45 degrees, your vectors will like coincide with the axis, and that will bring you a lot of convenience. So yeah, that's similar to the what the canonical transformation does. It just simply transform the coordinates, so you could make your equations more elegant, and through the equations you could make your motion more, you could make your motion more predictable. I believe what I talk about so far is quite abstract, so here I'm going to give an example that could help you guys connect all these concepts together, and also it could show you what the show you clearly that the advantage of Hamiltonian formalism. So how convenient would the equations of motion become if you use this formalism. So the type of problem I chose is central potential field problem. The feature of this type of problem is that the force center is fixed, and the potential energy term, the V, depends only on the distance between the object and the center. So there are a lot of like physics problems that belongs to this type of problem, including the Kepler's scenario and also the isotropic harmonic oscillators. So we're going to talk about general type of the problem, but in 2D. So the coordinates the first set of coordinates we chose is r and theta, since the whole problem is symmetric about the origin. So the r and theta representing the distance between the object and the center, and the angle between its location and the polar axis respectively, and we can use this set of coordinates to write out the Lagrangian of the system, which is equal to the kinetic energy minus the potential energy, and you obtain this expression. With the Lagrangian, you can then calculate the two canonical momentums, pr and p theta. Then, with the Lagrangian, we can also write out the Hamiltonian of the system, which is p times the derivative of q minus l. So you will obtain this expression. So I further simplified the expression as this, since in terms of pr and p theta, which could help us see which quantities are conserved. So we then sub the Hamiltonian into Hamiltonian's equations, which is the derivative of p is equal to negative partial of h over partial of q. So here we discover that p theta, the derivative of p theta, which is equal to negative partial of h over partial of theta, will become 0 because the Hamiltonian does not explicitly contain the coordinate theta. So yeah, this is conserved. And also I noticed that the total derivative of h over time is equal 0 as well. So here I used Poisson brackets. Remember what I talked about before? So Poisson brackets can be used to calculate the rate of change of the variable f that does not explicitly contain time. So here I'm not really sure whether the Hamiltonian whether the Hamiltonian depend on time or not. So I added the term partial of h over partial of t, but you could check that the Hamiltonian does not explicitly contain time. So the total derivative of Hamiltonian over time is 0 as well. So here then we'll use a very important theorem called the Louisville-Arnold theorem. What this theorem essentially is saying is that if a system in which the degree of the freedom is equal to the number of integrals of motion, then the system is integrable. By the term integrable. So by the term integral, it means that the system is perfectly solvable and perfectly predictable. So you could like predict any the state of the system at any time. Yeah, so that's a very good thing for us physics learners. So let's check in this case. So the degree of freedom is 2, because we only need 2 coordinates to describe the location of a particle, and the number of integrals of motion, which means conserving variables, is 2 as well, since we already have p theta, which is conserved, and h Hamiltonian itself is conserved as well. And also I forgot to mention another requirement is that the integrals of motion must be mutually in evolution. By the term in evolution, it means that for any 2 of the integrals of motion, their Poisson brackets must be 0. So let's check here. Let's sub in h and p theta into the Poisson brackets, and you guys could check the result is 0. So that satisfies our problem. So the problem of the central potential field problem is integrable, and I'll later show you guys how convenient it was. Next, we'll use another very important thing called the Hamilton-Jacobi equation. This equation is actually connects to a concept called generating function, which I didn't really talk about previously. So generating function. So remember the requirement for the canonical transformation, the pullback of phi on on omega must be equal to itself. So let's write omega. So since omega is the exterior derivative of theta, like that. So we can write it as this. And since the pullback is interchangeable with the exterior derivative, so that would be the equation would become this. So so actually theta we would discover that actually this allow for difference of a total exterior derivative. So it's kind of like in my first video I talked about Lagrangian, and I talk about that Lagrangian can allow for a difference of a total derivative, because that term will automatically vanish when we're doing the variation. So here comes a very similar thing. So when when the theta differs by a term of df, since if you sub this into this, you obtain something like d squared f, and this term is automatically 0 since you are applying the exterior derivative on a thing twice. So you get a 0. So so this df, which is something that could induce a type of like successful canonical transformation, and there are 4 types of f. This is f1. There's f2, type 3. The first one, this is small p, by the way. Type 4. So you will notice that since the canonical transformation brings the previous coordinates small q and small p to big Q and big P, which are respectively functions of old Q and P. So you will the generating function must like act as a bridge, like connecting the two set of coordinates. So you could choose one of the one of the old coordinates and one of the and one of the new coordinates, and yeah, so and you could connect the two set of coordinates together by using sort of equation. So what is this? What is that specific equation we use? So let's consider the action for now, the action of the system, which is s equal to L dt, and L, since L is equal to p dq minus h dt. And in this case, we denotate this as the tautological one form in extended phase space, because we have this term which implies that the Hamiltonian may change over time. So this is the extended phase space, because in previous context we just assume that the Hamiltonian does not explicitly depend on time. So here the theta may seem different, but it's still the tautological one. It's tautological one form, but however in a different space. And we write the new Hamiltonian as k. So since the 2 form is preserved, you would obtain something like this. And that is what I just talked about. You could allow for the exterior derivative of something f in this here, as long as the rest, and because after you take the exterior derivative on the both sides, this term will vanish. So yeah, that's the generating function. So let's now so in this case, the Hamilton-Jacobi equation, the s is actually a type 2. Type 2 generating function. So let's just write it out. Q P T, and it's differential. This term, the right hand side is expanded. This term is partial of f2 over partial of q dq with its indices. Big pi plus partial of 2 over partial of t dt. Okay, and then we can equate the several sides. You would obtain dqi. So pi is equal to partial of f2 over partial of qi, since like this term is equal to this term, and the dt term, h is equal to k minus partial of f2 over partial of f over partial of t. So yeah, and if you take closer look at this, since we have a new Hamiltonian, so and we set a new Hamiltonian to as 0, because we'll see why that would be, like we set this to 0, and we will see like why it will be useful later, and we will obtain this. We'll obtain this equation right over here. So this is the equation, it's called Hamilton-Jacobi equation. So just the equation that is derived from the type 2 generating function. So you guys would see why this equation will become out very very convenient. So you change all the p-values, the big p-values, to the partial of s over partial of qi. So you automatically like assume that s satisfies pi is equal to partial of s over partial of qi, and that is over here. All right, and like in this case, our q generalized coordinates are r and theta. So s would be functions of r, theta, and t, and our Hamiltonian, which is over here, and you could change it. You could write it as this. Okay, so here comes the advantage of introducing s, because it will help us separate the variables. So since s is a function of r, theta, and t, we can separate it as since we only have a part of s or part of t here, so we can separate it as one function w, which is the function of r and theta, and the other one is the term negative e times t, and e is a constant, and you guys would obtain this equation. So the reason why I use the letter E is that it stands for energy, and it is actually this equation is exactly the expression for Hamiltonian. So this E is valid, and then we noticed we had just talked about that the p theta, which is actually the angular momentum, is conserved. So theta would be a cyclic coordinate. I think I talked about the concept of cyclic coordinate at the in my previous videos. So anyway, you can that means that you can pick the coordinate theta out. So the partial of s over partial of theta would be a constant, because here we just mentioned that pi is equal to partial of s over partial of qi. So we can obtain this. So partial of w over partial of theta would be constant as well, since w would be the only function in s that depends on theta, and we denote this as m, because m stands for angular momentum. Okay, and then our equation could be further simplified with w. We can further separate w, because the theta would be a cyclic coordinate and it could be sorted out. So the new wr function will be depend solely on r, and we can write it as the total derivative of wr over dr here, and you will obtain this expression. And the rest of the we can then pick out the total derivative term and write it as this, and then integrate it to obtain the expressions for wr and then w, and then with the expression for w, we can then write out the expression from s, which is equal to this long thing. Okay, up till here, we have successfully obtained the expression for s. Since now you have already obtained the whole the complete expression for s, and s is as I just mentioned, it belongs to a type 2 generating function. So you could observe that we use the conserving quantities m and e in the expression. So m and e are exactly the big P here, the big P, or the new chosen momentum to be the new coordinates. Okay, so the big P1 would be E and big P2 would be M. And how would we obtain the new coordinates? It's easy. We just take the partial. The new QI would be partial of S and over partial of P, big PI. Why is that? So let's take a look at this here again. So here we already cancel out here and here, 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 and here. So what is left is big pi dqi plus partial of f2 or partial of big f2 or partial of big pi dpi. So you would discover that this is actually kind of similar to the total differential of pi qi, and that is something on the real numbers. So this is equal to 0. So to satisfy that, this must be equal to qi, big qi. So here we have already obtained it, and with these we have already have the expression for s and p1 p2. We can then calculate by taking the partial derivative to obtain the expression for q1 big q2. You obtain some expression that's kind of disturbing, but actually it's very very useful. Why is that? So since I just we just let the new Hamiltonian k to be 0, because here the Hamiltonian Jacobi equation, this is actually the new Hamiltonian, so we let this to be 0. So, and we also have this conserving quantities p. Both p1 and p2 are conserved. So in the new Hamiltonian system, so the partial of k, which is new Hamiltonian, over partial of q is equal to the value of p, the derivative of p, and it was equal to 0. And what would this bring us? It means that the k, the Hamiltonian function, the new Hamiltonian function k, will depend solely on the p's, since its partial derivative of k over partial of q is equal to 0. Right? And since this is 0 as well, and so partial of k over partial of p, which is equal to the derivative of q, will be 0 as well. So in this new set of coordinates, both q and p, both q's derivative and p's derivatives are 0. So it means that if we're given any point q, p on this new set of coordinates, we already have the whole motion, and the system is like still in this set of coordinates, and that is very magical. I know it is, and this is kind of like surprising, because a moving system suddenly becomes still when we just apply a set of canonical transformations. But that is good in a sense, because it could help us solve the equation, because all we need is a 1 point and we know the whole motion in this set of coordinates. So that is one canonical transformation we make, and here I have another one. So here this new point, this wait, let me write it out. So this set of coordinates, big q1, big q2, e and m, are advantageous while we're trying to solve the equation. But here I want to introduce another thing called, that is more generally more used, called action angle coordinates, and that is like, I think that's more important than this one. So the ultimate goal in this case is to transform qp into set of coordinates called j and phi, which are separately called action and angle, and such that the derivative of the derivative of j is equal to 0 and the derivative of phi is equal to a constant. So why would that be helpful? Because then you will be the system, you would not only make the system easy to solve, you will also find you're also like, you're not like facing a still system, because in this case, in this q1 q2 em system, you cannot really predict the system if you're given a time, and you cannot really like predict the evolution of the system, because the whole system is like still. But in this case, you're like preserving the part of the part of dynamic, because this phi thing is like constant. So you could obtain something like this, plus omega times t. So this is like a periodic motion, and however the action, the derivative of the action is equal to 0, and this is fine. Actually in differential geometry, you're actually working on a torus, an n-dimensional torus, depending on how many coordinates you have, because the dimension, if you have like n action variables and n action variable, n action variables and n angle variables, you have total of 2 n variables, and n of them is fixed, because the derivative is 0, so they are constant, and leaving the rest of n is like, but the rest of the n is like doing periodic motion on the new phase space. So actually since it's periodic, so you could like abstract it into a sphere, which is S1. So if you get all these S1 together, you obtain an n-dimensional torus. So that is a very like elegant thing to think about, and that kind of so this is like the ultimate goal for a lot of scenarios. And if you could simplify the motion to that sense, you would obtain a very, not only have you like simplified the problem into a very easy case, you could also like make the whole thing predictable, and that is the ultimate goal for a problem if it's integrable. Let's take a look at how this is done in a brief. So first, you take a look at the tautological one form, lambda, which I write it as lambda to distinguish between the theta direction. So lambda is equal to PDQ, and you write it into the separate directions, and you define the action variable ji. We define as this. So the reason it's defined as that is because, first of all, it accounts for the periodic motion that we hope to get, like since the derivative of phi is a constant, so we hope to obtain such periodic motion. And then the reason why we take the tautological one form is that if we think about the Lie derivative on the Hamiltonian field of the one form lambda, you would actually get an exterior derivative. So since it could be written as the form of an exterior derivative, its integral over a closed loop will always be 0. So that's why it satisfies. And then after you construct the two action variables, you're already halfway there. You would only need a new generating function s, and then you could write out the rest of it, and you would yield the correct angle variables, and that's how you do that. So yeah, that's the end of today's content, and we talk about a lot of things. Basically, the most of them is about how, from like inventor's point of view, how we construct everything in the phase space, and why we define this, why we define that, and why this simplex structure is very convenient. So I really appreciate you guys if you have already watched here, and hope you guys enjoyed it. Thank you very much.